Hello, welcome everyone. So good to see you here. My name is Giovanna Scorsone. I'm the Education and Public Engagement Manager here at the Aga Khan Museum, and I'm very happy to welcome you here to this talk as we hear from Dr. Jamil Shariff on the moon and humanity. The moon is such a universal thing. It's wonderful that we can all look up at the sky from wherever we are, from whenever we are. So many cultures have incorporated it into their folklore, their science, their understanding of the world, whether it's from here in the place where the Aga Khan Museum sits, in the traditional territory of the Anishinaabe, the Haudenosaunee, and the Mississaugas, or whether it's the historical birthplace of Islam in Mecca. So it's one of those things that ties us all together, ties humanity together. And you know, the expression of art and science together is something that's really exciting for us here at the museum. In fact, it's a central theme of our beautiful moon exhibition upstairs, so I hope if you haven't seen it yet, you'll have a chance later. But we're very happy today to welcome Dr. Jamil Shariff to talk to us today. He's an astronomer and a public speaker with a PhD in astrophysics from the University of Toronto. As a part of his research, he lived at the McMurdo Station in Antarctica, and for 3 months, where he helped build and launch a telescope into the stratosphere on a high-altitude helium balloon. This telescope, called SPIDER, was designed to measure the glow left over from the heat of the Big Bang. He's a member of technical staff at MDA Corporation, where he works on robotic hardware for space exploration, including a new Canadarm for the Lunar Orbital Platform Gateway, which is super exciting. When it's constructed, this space station will orbit the moon and will be the most distant human outpost ever to exist. So a bit of a different sort of speaker for us here at the Aga Khan Museum, but super exciting because we're always celebrating how science and art are actually completely integrated in our understanding of humanity. So please join me in welcoming Dr. Jamil Shariff to the stage.
Okay, thank you very much for that kind introduction. Can everyone hear me? All right. So, just got to get the slides queued up. There we are. I thought I would start today with one of the most famous and iconic photographs in human history. This image has come to be known as Earthrise, and it was taken by the astronauts of Apollo 8 in December 1968, just over 50 years ago, as they became the first humans ever to orbit around the moon. And this image of our planet as this fragile blue orb in the cosmic void totally altered our perspective as a society. Some people even credit it with kicking off the modern environmental movement. So I'd like you to keep this locale in mind, lunar orbit, because we will return to it by the end of this talk. But the first step in our journey today is actually the distant past. So today I'd like to talk first about cycles, events in nature that repeat at regular intervals. One such cycle is illustrated nicely here by this long exposure photograph of star trails over the Atacama Desert in Chile. The cycle being, of course, the rotation of the Earth over a portion of the night. And of course, I'd be remiss if I did not mention that today we are very close to the summer solstice, which is a very important event in the cycle of the sun. Now, first of all, it's the longest day of the year, and second, it's marked by many as the beginning of summer, which has been a long time coming in Toronto. We all know this famous stone monument that was built by Bronze Age people in what is now England. And this is a photograph taken on the summer solstice last year, showing that the structure was actually constructed so that certain stones would align with the rising sun on the day of the solstice. And construction at this site may have begun as early as 3000 BCE. That's kind of astounding when you think about it, because it means that at least 5,000 years ago, ancient people understood specific details about the natural cycles of celestial objects. And not only did they assign their own cultural and religious significance to those cycles, but they used them to mark the passage of time. Nowadays, of course, we understand that the changing of the seasons happens because Earth's axis, this imaginary line that goes between the North and South poles and which the planet spins around, is tilted in comparison to its orbit around the sun. So at this point in the orbit, the northern hemisphere is tilted towards the sun, leading to more daylight hours and more direct illumination. At this point, it's the southern hemisphere's turn to experience that. And at these 2 points, the equinoxes, you can see that the axis is neither tilted towards nor away from the sun. So both hemispheres receive equal illumination. Now, in case you've noticed something strange about this diagram, I found it online and I really liked it, but it's from the Australian Government Bureau of Meteorology, so I have to fix it for us here in the Northern Hemisphere. But it's a good diagram, I think. So if you're an ancient civilization and you're looking to construct a calendar, the length of the solar cycle, which is called the tropical year from solstice to solstice, is a pretty good candidate to be a basis for such a calendar. And so far, it's the only one that we've got on our list. But another really prominent cycle, of course, is the cycle of the phases of the moon. Now, this is illustrated here by this wonderful piece from the exhibit, which is a drawing taken from a manuscript that was written in 16th century Turkey, in Ottoman Turkey. So it shows us what we all know, which is that as the moon moves around the Earth, it gets illuminated by the sun from different angles. So the side of the moon that's facing towards us receives a different amount of illumination depending on the time of the month. So when you hear the word month, you should really think moonth. And we go from new moon to first quarter to full moon to last quarter and back to new moon, and that's the cycle. Now, a natural question to ask is, how long does this cycle take? So I thought I'd ask you, the audience. This is a poll for you. Here's the question, okay? What number of days is closest to the length of the lunar cycle? So just by a show of hands, how many people think it's A? 0 people. Okay, how many people think it's B? A few here and there, quite a few. And votes for C. All right. So the answer is that it's a bit of a trick question. I talked about 2 different cycles. One was the moon orbiting around the Earth, and the second one was cycling through a full set of phases of illumination. And it turns out these 2 things are not exactly the same. And I have this handy diagram here, which is very much not to scale, to illustrate this. So here we have the Earth orbiting around the sun, and we also have the moon orbiting around the Earth. And you can see that I happen to have picked a day where the sun, Earth, and moon are all in line. So this is going to be a full moon because the side of the moon that faces towards Earth is also directly in line with the sunlight and directly illuminated, okay? Now let's say, for the sake of argument, that it just so happens also that the moon happens to be lined up with some star that is located that away, okay? So if you look at the full moon on the sky, you say, oh, look, it kind of coincides with the location of some star. It doesn't matter which one, right? Now, over the course of a month, the moon is going to complete one full orbit and return to the same spot. But during that same interval of time, the Earth will have moved a little bit in its orbit around the sun, like so. So after completing one full orbit, the moon has returned to being lined up with that star. But is this going to be a full moon? Well, the answer is no, because the moon is no longer directly in line with the sun, and it actually has to move a little bit farther before we get back to a full moon, okay? So a full orbit happens after just over 27 days, and getting back to the full moon happens at day 29 and a half. So we actually have two lunar cycles. The sidereal period is the time needed for the moon to get back to the same constellation on the sky. Sidereal just means having to do with the stars. And then the synodic period is the time needed to get back to the same phase, so full moon to full moon, for example. So for all of those of you who voted for 28, I'm sorry, better luck next time. Both of these cycles were known to the ancients, but it's really the synodic month that would be a leading candidate for timekeeping, because observing the phases of the moon and recording them is relatively easy. So now, if we get back to our list of candidates, we have two candidates for the construction of a calendar. On the one hand, a calendar based on the length of the solar year is really convenient because it means that your dates actually tell you useful things like when to plant, when to harvest. On the other hand, the lunar month provides a nice smaller block of time into which you can partition your calendar year that's easily traceable and repeatable. And observing the phases of the moon doesn't require as much painstaking effort as trying to measure the length of every single day of the year using the height of the sun or something. So is there a compromise that would give us the best of both worlds? Well, if you look at these numbers, you can see that, you might eventually see that the problem is that a whole number of lunar months don't fit nicely into the solar year. 12 lunar months is about 354 days. That's 11 days too short. 13 lunar months is about 383 days. That's too long. I made a visualization to try to illustrate what's going on. I don't know if it will make things clearer or less clear, but we'll give it a shot. It turns out that mathematically, anything that repeats cyclically, you can represent it as a wave. So on the top, this blue wave, this long, slow wave, represents the cycle of the seasons. We go from summer solstice to fall equinox to winter solstice to spring equinox and back to summer solstice. On the bottom here, we have this orange wave representing the cycle of the phases of the moon. So here we go from full moon to last quarter to new moon to first quarter and back to full moon. And you can see that the bottom wave is repeating much faster than the top one. Almost 12 times faster, but not quite exactly, unfortunately. And I just so happen to have picked a time at the beginning here when both waves are at their peak, which means that it's both a full moon and the summer solstice at the same time. And the question is, when will these two events next coincide? In other words, as I scan to the right, which is forwards in time, at what point will the peaks of these two waves be lined up again? Well, you can see that in year one, they don't line up. The 12th full moon happens a little bit before the summer solstice, 11 days before, as we just discussed. And to make a long story short, they don't line up in year 2 or year 3 either. So far, it's not looking too good as far as getting these two waves to sync up again, right? Well, the good news is that I kept searching forwards in time so that you wouldn't have to. And I found out that in year 19, what do you know? The peaks line up again. And here's a zoom in on that, just to show you that this alignment is actually pretty good. Now, what's really funny about this is that this 19-year cycle that I have sort of just discovered for us by writing a fancy computer program was known to the ancient Babylonians 3,000 or 4,000 years ago. It's called the Metonic Cycle. It's named after a particular Greek astronomer, ancient Greek astronomer, who developed it, but all of the sources I read seem to agree that it must have been known to humanity far earlier than him. And the reason why it works is because 235 lunar months is very, very, very close in length to 19 solar years. You don't have to take my word for it. You can take your phone out and check. Little did you know that this talk would involve both quizzes and homework, but this seems to be where we are right now. So before you rush off to get into the calendar-making business, you should realize that we're not quite finished yet. What we've learned is that if we could construct a lunar calendar that repeated on a cycle of 235 months, then our calendar dates would never drift too far back and forth relative to the seasons, and they would reset to sync up with them almost perfectly every 19 years. Now, the problem is 235 months is not a whole number of calendar years if your calendar years are 12 months long, right? So a way around that problem is in some of the years, you insert an extra month. So in 7 out of the 19 years, you have 13 lunar months, and in the remaining 12 years, you only have 12 months. And that'll get you up to 235. So this process of inserting extra periods of time in order to remain synchronized with nature is called intercalation, and pretty much any calendar system you could come up with needs to do this. If you have a calendar that inserts these extra leap months in order to take advantage of the Metonic Cycle, it's called a lunisolar calendar. So the Jewish calendar operates exactly on this scheme. I think the motivation for constructing it that way was so that the holiday of Passover would always fall in the springtime. And over the course of history, there are many, many cultures that have developed calendars that are essentially lunisolar in one form or another. Now, in contrast, the Islamic calendar is a purely lunar calendar, although there is some evidence that nomadic communities in Arabia prior to the origin of Islam may have used lunisolar calendars from time to time. But the Islamic calendar itself just has 12 months, and each of them is either 29 days or 30 days. And how do you figure out whether a month is going to be 29 days or 30 days long? Now, there are some sects or communities within Islam that use a pre-computed, pre-tabulated version of the lunar calendar, where if it's an odd-numbered month, it has 30 days, and if it's an even-numbered month, it has 29 days. But I think it's fair to say that traditionally, in the majority of the Muslim world, the beginning of a new month has actually been based on the visual sighting of a crescent moon in the first or second evening after the occurrence of a new moon. So what that means is it's impossible to predict in advance when this month will end and the next one will begin. But it also means that the system is self-correcting. Let's say the end of this month is delayed because viewing conditions were bad. Well, what that means is next month or some other month down the line, it will necessarily be a shorter month because you're going to look up and say, oh, look, it's already a new moon, right? Now, the Islamic calendar in its current form began in what is for us the year 622, and that was the year of the Hijrah, which was the migration of the Prophet Muhammad from the city of Mecca to the city of Medina, he and his early followers. So the current year, according to the Islamic calendar, is the year 1440 AH, after the Hijrah. So if you go to the exhibit, you will see that calendar dates will be given in this format and also with their traditional Western calendar years alongside. Now, obviously, the moon plays a very significant role in the Islamic way of life in terms of the determination of prayer times and times of festivals. And that is a major theme of the exhibit here and some of the other programming. So I encourage you to take advantage of them to learn more about that. For today, I would like to move on because as an astronomer, I really wanted to address how the moon affects us just by virtue of its physical presence as a relatively large planetary body that's relatively close by. I would say that the moon is close to unique in our solar system and may actually even be quite rare in the galaxy as a whole in terms of how large it is in comparison to the planet that it's orbiting around. Because you see, the moon is more than a quarter the size of Earth. And having such a large natural satellite so close by for almost the entire 4.5 billion year history of our planet has had some very, very significant effects. What I'm showing here is a study that was published in a scientific journal saying that the presence of the moon probably helps stabilize Earth's axis of rotation. So you remember earlier I mentioned that it's actually tilted. And the angle of that tilt is pretty steady. It's at 23.5 degrees doesn't vary by much more than a degree in any direction over the course of millions of years. And there are even some theories that just that minor variation was enough to be responsible for the ice ages that we've had throughout Earth's geologic history. Now, what this paper is saying is that if the moon hadn't been there, the variations in the tilt of the axis could have been much more extreme. We could have gone over the course of a few million years from no seasons to very, very extreme variations between the seasons. And some scientists have even theorized that without the moon there to act as a climate regulator, the extreme differences in climate could have basically hindered the development of life on Earth or significantly altered how it went. So that's a huge impact. Another huge impact of the moon, and the very last natural cycle that I'd like to discuss, is the cycle of the tides. So I think most of us are probably familiar with this idea that the oceans change level and that most coastal areas see 2 high tides and 2 low tides over a period of 24 hours. And if the moon were not present, the only place that the force giving rise to those tides could come from would be the sun, and it would only be half as strong. But in order to understand how the moon's gravity causes the tides in the first place, we need to understand what tidal forces are. So I thought I would illustrate this using a very extreme example. If you ever have the misfortune of falling into a black hole, and I pray that it does not happen to you, you will find yourself being stretched out, much like our astronaut friend here. And the reason for that is everything has gravity. Everything pulls on everything else. But the strength of the pull depends on how far away you are from the thing that's doing the pulling. It depends on distance. And our astronaut friend here is in a situation where the strength of the black hole's gravitational pull on his feet is quite a bit stronger than the strength of the black hole's gravitational pull on his head. So our friend here will become infinitely elongated, and we astrophysicists have a very scientific term for this. It's called spaghettification. Now, a much more, shall we say, terrestrial example has to do with the tidal forces on the Earth due to the moon. So the side of the Earth closest to the moon experiences a slightly stronger gravitational pull from the moon than the side that is farthest from the moon. So as a result, the Earth itself kind of becomes elongated. And since the oceans flow more easily than land, it's really the oceans that form into these tidal bulges, grossly exaggerated here, that appear on opposite sides of the planet. So if you're at any location on the surface of the Earth, as the Earth spins, you pass through a tidal bulge twice a day. We go from high tide to low tide to high tide to low tide. Now, the only wrinkle here is that because of friction, the bulges actually get carried along with Earth's rotation a little bit, and they end up slightly ahead of where the moon is. So the actual picture looks like this. And what that means is that the gravity of the moon is going to pull backwards on this tidal bulge a little bit, actually slowing down the rotation of the Earth. So because of tidal forces from the moon, the length of the day is increasing. Now, it's only increasing by 1 second over 50,000 years or something like that, but nonetheless, the day is lengthening. And every action having an equal and opposite reaction means that the gravity of this bulge pulls a little bit on the moon in this direction, boosting it up into a higher orbit. So the moon is actually receding away from the Earth by about 4 centimeters every year. All of this due to tidal forces. Now, if there are tidal forces on Earth due to the moon, then there must necessarily be tidal forces on the moon due to the Earth. And initially, the situation was very much like we just went through. There were these tidal bulges, they were slightly ahead of where the Earth was, and the Earth was pulling back on them, slowing down the spin of the moon. The difference is the Earth being so much larger than the moon the effect was a lot stronger. So it already happened a long time ago that the spin of the moon was slowed enough that it became synchronized with how long it takes for the moon to actually go all the way around the Earth in its orbit. So what a consequence of that is that the bulges are always lined up along this line between the Earth and the moon. So there's no further slowing down of the spin. We say that the moon has become tidally locked to the Earth. So what that means is it always presents the same side of itself towards us. You can see that in this little animation. So you take a look at the blue arrow, that's the side of the moon that faces toward Earth. And in order for it to always face toward Earth, it must be the case that the moon is spinning. So if you just focus on that blue arrow, you'll see that it does do a full 360. The moon is spinning. It's just spinning at a rate that it takes the exact same amount of time to spin around once as it takes to go in one full orbit, okay? All right, so this animation, I think, nicely sums up some aspects of the moon that we've been talking about. What this is showing the moon as it appears from Earth every hour over the course of a full lunar month. And you can see the changing of the phases as the moon is illuminated from different sides by the sun. You can also see that it more or less presents the same face towards us, but it wobbles a little bit. And that wobbling is called libration. And finally, you can see that it appears to be getting larger and smaller. And that's because the orbit of the moon around the Earth is not a perfect circle. It's elongated into an ellipse, which means that depending on where it is along its orbit, it may be farther away from or closer to Earth. And even though this is a computer simulation, it actually uses real data taken by the Lunar Reconnaissance Orbiter, or LRO, which is an automated spacecraft that's been in orbit and observing the moon since 2009. And LRO had this laser instrument that it used to map out how high all these surface features are. So that means that the lengths of the shadows of those features are really, really accurate in the simulation because we have detailed 3D information about the surface of the moon. So I think that brings me nicely to the second and last part of my talk, which has to do with our continued exploration of the moon and perhaps even of Mars. Now, I'm very fortunate to have become part of a new and exciting project in the area of space technology and exploration. It's referred to variously as the Deep Space Gateway, or more recently, the Lunar Orbital Platform Gateway, which I think is a little bit more of a cumbersome name. But regardless of what you choose to call it, here is what it is. We have the Earth, and we have low Earth orbit, about 400 kilometers up. And that is where the International Space Station currently is. Now, like all diagrams in my presentation, this one is very much not to scale, but about 1,000 times farther away, we have the moon, and we have various possible orbits of a certain type that you can think of as high orbits, high halo orbits, represented by these colored lines. And we picked a particular one, and that is where we are proposing to put a new space station, the Deep Space Gateway. And you can see that the concept for the Deep Space Gateway is that it would be quite a bit smaller than the International Space Station. Here's a side-by-side comparison. And you can also see that, like the International Space Station, it would be constructed in stages with different modules that dock together to form the full thing. So there would be one module for power and propulsion. There would be a module for communications and for refueling and for deploying scientific experiments. And then there would be a couple of modules that actually are pressurized with air in them to provide a habitat for astronauts. And there would be visiting vehicles like this Orion spacecraft, bringing visitors and supplies, and also going off on forays out into the solar system. You could think of them sort of as practice runs for a Mars mission where we progressively go deeper and deeper out into space. And that brings to light one of the key purposes of the Deep Space Gateway, which is to be sort of a stepping stone on our path towards a Mars mission. Now, it may not necessarily be a physical stepping stone along the journey, although that's possible, but more importantly, it would use operating in the space between Earth and the Moon as a stepping stone in our knowledge and technological capability. Because here's the thing. If you're on the ISS, the International Space Station, you have near constant communication with Earth. You have access to new supplies and provisions brought up by spacecraft. And if there's an emergency, an astronaut can be transported back to Earth within 24 hours. Compare that with a Mars mission. Round trip, it could take 3 years, during which astronauts have delayed or no communication with Earth, no resupply of air, water, food, and a lot more danger from radiation and other environmental factors. So the idea behind the Gateway is that it would actually only be crewed 1 month out of the year, and the rest of the time, there would be no humans on it. It would have to operate completely autonomously. Not only that, but even when humans are there, the communication window with Earth will be restricted to be 8 hours in a week. Outside those 8 hours, you're on your own. So, the need for this degree of automation is where Canadian technology really comes in. You've seen a hint of it here, but the plan for the Canadian contribution to the Deep Space Gateway is what are being called at the moment Deep Space Exploration Robotics, or DSXR. And what they consist of is a set of robotic arms. We have one large one called the Exploration Large Arm, or XLA, that is a manipulator with 7 joints, okay? And then we have another smaller dexterous arm that is able to do finer, more detailed work. And finally, we have a set of robotic tools and adapters that would attach onto the ends of the arms to enable them to do various tasks. And those tasks could include things like capturing a visiting vehicle or releasing visiting vehicles, docking and undocking them from the station. It could include attaching to different components or modules of the gateway and moving them around from one place to another. And very importantly, it includes completely automated repair and maintenance of the space station. So I just wanted to show you an example of this in action. Here is a computer animation of DSXR unloading cargo and installing it somewhere. Here's an animation of it putting a robotic tool back into storage. And this is one of my favorites. Here's an animation of it walking around on the station. There are these various attachment points that allow it to walk end over end so that the tip becomes the base becomes the tip, right? The tip becomes the base, and in this manner, it just inches its way along. And actually, the Canadarm2 on the current space station can already do this. And here, swapping out a module for repairs, let's say, like a battery pack. All of this with no human intervention. So at this point, you might be wondering, who's going to build all this? Canada has committed to the project. And the company that I've begun working at just as of January of this year, McDonald, Detweiler and Associates, or MDA, was the contractor to the CSA, the Canadian Space Agency, for the study phase of the project, the phase that led to all the concepts that you see here. MDA is going to be submitting a competitive bid in the hope of also becoming the contractor for the design and construction phase of the project. And an advantage that MDA has is 40 years of experience in this realm. MDA designed and built the original Canadarm, which flew on the space shuttle and was first launched in 1981. MDA also designed and built Canadarm2 and Dexter, 2 robots that are currently operating on the International Space Station as we speak. Now, Canadarm2 and Dexter actually fulfill a very similar role on the ISS to what DSX-R is envisioned to fulfill on the Lunar Gateway. The difference is that Canadarm2 and Dexter require that they be controlled by a human operator right now, whereas DSX-R is envisioned to be completely automated. And you may not even realize it, but you actually see Canadarm2 and Dexter every day on our currency. So in summary, if everything goes according to plan, in the mid-2020s and beyond, we will be returning to this vista, to lunar orbit. The moon, our constant companion, having inspired us to continue to expand our knowledge, to continue to expand our presence in the universe, and to continue to challenge ourselves to solve difficult problems for humanity. I don't know about you, but I can't think of a better time to be in, and I can't think of a better place to leave you today. So thank you very much for joining me today. Thank you.